Here is a combined summary of the 2 pages. The paper explores the application of quantum dynamics to machine learning, establishing a theoretical framework for investigating machine learning iterations through quantum and mathematical theories. The authors reformulate the iterative process of machine learning into a time-dependent partial differential equation, drawing from the Schrödinger equation and potential energy equivalence relationship. This approach not only presents a rigorous theoretical foundation for machine learning but also holds promise for supporting the implementation of machine learning algorithms on quantum computers. The authors highlight the significance of dynamics theory in machine learning, citing pioneering work by Metropolis in 1953 and subsequent developments. They discuss the potential of a quantum dynamics framework for optimization problems, citing their own research and the successful application of quantum dynamics in artificial intelligence, including the D-wave quantum computer. The cornerstone of the kinetic theory of machine learning lies in formulating the kinetic equations that govern the learning process. Quantum dynamics, rooted in the fundamental laws of motion, offers a compelling framework for this purpose. The Schrödinger equation, the core of quantum dynamics, elegantly captures the probabilistic laws of motion through a deterministic, time-dependent partial differential equation. The authors introduce the quantum dynamics framework, QDF, for optimization problems, which is illustrated in Figure 1. The QDF is built around the Schrödinger equation, with the objective function serving as the potential energy. The framework encompasses various components, including the diffusion model, Softmax and Sigmoid functions, and Wick rotation, which establishes a relationship between quantum dynamics and thermodynamics. The authors demonstrate the applicability of the QDF to machine learning, validating the proposed quantum dynamics equations and highlighting the potential for further development and implementation on quantum computers. Here is a combined summary of pages 3 and 4 of the research paper. The quantum dynamics framework, QDF, interprets the iterative process of an optimization problem as a quantum dynamics process, where the objective function f, x, is considered as the potential energy term v, x, in the Schrödinger equation. This leads to the equivalence v, x, equals f, x, transforming the optimization problem into one of solving quantum constraints. Specifically, this approach seeks the ground state wave function of a quantum-bound state, with the corresponding quantum dynamical equations for the optimization problem expressed as the time-dependent Schrödinger equation. In the context of machine learning, the optimization objective is to find an optimal combination of connection weights in the parameter space. The generalized objective function zeta, x, formally represents the mathematical relationship of the objective function within the neural network's parameter space, regarded as a potential energy term in the Schrödinger equation. The Schrödinger equation is thereby transformed into the quantum dynamics equation for machine learning, which can be interpreted as a system of quantum-bound states defined by a potential energy function, zeta, x. The Hamiltonian operator of the system is given by h equals d squared partial differential x squared plus zeta, x, where the parameter d determines the magnitude of the system's kinetic energy. The system can be annealed by gradually decreasing the value of d. The quantum dynamics equation of machine learning predicts that the iterative process may involve 2 major iterative loops: the quantum annealing process and the time evolution of the system towards the ground state under a fixed kinetic energy condition. To approximate the quantum dynamics equations, a Taylor expansion of the generalized objective function zeta, x, is used. The zeroth-order Taylor approximation reduces the quantum dynamics equation to the free electron equation, characterizing the quantum dynamics of an algorithm when the information about the generalized objective function is entirely unknown. The first-order Taylor approximation represents the gradient of the wave packet as the electron moves to the position x, obtaining the current constraint potential zeta, x, as partial differential zeta, x, partial differential x. This dynamic mirrors the algorithmic process of gradient descent optimization. The classical approximation of machine learning quantum dynamics equations is proposed to address the challenges of simulating wave packet dynamics in quantum mechanics. The paper discusses the application of quantum dynamics theory in machine learning, particularly focusing on the convergence analysis of machine learning algorithms. It starts by explaining how quantum dynamics equations can be used to describe the iterative process of machine learning, transforming it from a wave packet dispersion to a classical diffusion process. The Green's function for the unidimensional diffusion equation is introduced, describing the diffusion process of a point source. This concept is then connected to the Gaussian stochastic diffusion process in the parameter space, where the information about the generalized objective function is unknown. The Fokker-Planck equation is discussed, which describes the dynamics when the derivative of the generalized objective function is accessible, allowing for gradient descent. The paper also delves into the convergence analysis of machine learning, showing how the iterative process converges to the ground state as the energy of the system decreases. The Softmax and Sigmoid functions are derived from the classical diffusion reaction equations, highlighting their connection to the kinetic energy of the system. Overall, the paper provides a comprehensive understanding of how quantum dynamics theory can be applied to machine learning, shedding light on the fundamental processes and algorithms used in the field. The state of the system at time tau is described by the equation ck phi k, x, express, minus ek tau, where ek represents the energy level and ck phi k, x, is the wave function. The initial moment of the algorithm's evolution is denoted by tau equals 0, and the probability of a state with energy ek can be approximated using the softmax function with respect to time, given by Peng approximately equals express, minus ek tau, and Airy summation I equals 1 express, minus a tau. This function dynamically evolves over time, with the probability of a state with low energy increasing as tau increases. A two-energy approximation of the system is made by reducing the system energy to two states, designated by A and E-flat, where A is the low-energy state corresponding to the superior solution and E-flat is the high-energy state corresponding to the inferior solution. The probability of occurrence of the low-energy state A is given by P approximately equals 1 plus express, minus increment E tau, which is a time-dependent sigmoid function. The diffusion model, a machine learning algorithm based on thermodynamic theory, is interpreted through the lens of quantum dynamics. The relationship between quantum dynamics and diffusion processes was initially explored by Anderson in 1975, who proposed the diffusion Monte Carlo (DMC) method for solving the ground state wave function of a molecule using a random walk. The DMC method exploits the isomorphism between the Schrödinger equation and the diffusion equation to compute the ground state wave function of a quantum system. In the context of machine learning, the quantum dynamics equations are analyzed, revealing that the zeroth-order Taylor approximation of the generalized objective function requires Gaussian sampling in the parameter space. However, direct Gaussian sampling is not permitted in the parameter space. The diffusion model resolves this issue by indirectly implementing Gaussian sampling through the Gaussian noise diffusion process in the learning space, which is an approximation of the Gaussian sampling process in the parameter space. The iterative process of the diffusion model is consistent with the theoretical framework of quantum dynamics in machine learning, with each denoising iteration analogous to a Gaussian sampling operation within the generalized parameter space. Here is a combined summary of pages 9 and 10. The diffusion model is shown to indirectly implement the Gaussian sampling diffusion process in the parameter space, eliminating the learning process of Gaussian noise and completing the mapping of the learning space to Gaussian sampling and gradient acquisition in the parameter space. This process is analogous to the classical approximation of the wave packet dispersion process in quantum kinetic theory. The quantum dynamics of machine learning suggest that an annealing process, which gradually reduces the kinetic energy, is necessary. This can be achieved by incorporating multiscale noise in the diffusion model, as demonstrated experimentally. The paper establishes the quantum dynamics equation for the iterative process of machine learning based on Schrödinger's equation and relates it to the thermodynamics equation through Wick rotation. The quantum dynamics equation is used to obtain the basic iterative process of machine learning through Wick rotation and Taylor approximation. The generalized solution of the equation yields the softmax and sigmoid functions commonly used in machine learning, providing a physical and statistical explanation of their significance. The quantum kinetic equations are used to give a kinetic interpretation of the basic iterative process of the diffusion model. The establishment of quantum dynamics equations for machine learning transforms the iterative process of machine learning into time-containing partial differential equations, achieving an accurate mathematical description of the machine learning process. This enables the use of mature theoretical systems in quantum mechanics and mathematics to carry out research on machine learning. The work presented in this paper offers a novel research perspective and a theoretical foundation for the precise establishment of machine learning. The theoretical framework is expected to provide a foundation for the implementation of artificial intelligence algorithms on quantum computers in the future. The references cited in the paper provide a comprehensive overview of the research in quantum dynamics, optimization algorithms, and machine learning.